Lesson 4, 2.4, Multiplying and Dividing Radical Expressions. When multiplying radicals, multiply the coefficients and multiply the radicands, okay? So multiply the coefficients is one step, and then multiplying the radicands is another step. You can only multiply radicals if you have the same index that's in front of you. Now, if we look at this right here, we're saying, okay, both of these are square roots. Okay, so that means that we can multiply these numbers together. Usually what we would have is we would have a coefficient out front, but we don't in this case. Well, actually we do. It's an implied 1, just like the index here is an implied 2. But what we can do is we can say, okay, the square root of 3 times the square root of 5 is the square root of 3 times 5, which is the square root of 15. Done. You've been doing this just kind of the opposite way before. You've been given the 15 and then you've had to split it into the mixed radical. But now we're getting entire radicals. We will find entire radicals and then simplify, but that's coming up. So in the case of having a coefficient and a radical, we multiply the coefficients first. 2 times 3. And then we multiply what's underneath the radicals, or we multiply the radicands. That's the better way of saying it. So then I have 2 times 3, which is 6, times root 3 times 3 is 9. Probably at this point you could have been like, oh, that's just 3. So then we have 6 times 3, which is simply 18. So sometimes when we multiply radicals together, we're going to come out with just a natural number or any integer. It doesn't have to have a square root or a radical in it. So simplifying expressions with numerical radicands. So that means that numbers are underneath the radical. So with this one right here, we have 2 times the square root of 6. The square root of 2 times the square root of 6. So we get the square root of 2 times 6, which is the square root of 12. Now here's another step. We've expanded it, so this is the expanded version, but we need to simplify. Now we're going to pull out our biggest perfect square factor. So we have 4 times 3, which is 2 root 3. If I went a little too fast here, the intermediary step here is the square root of 4 times the square root of 3, which becomes the square root of 4 is 2. What I'm going to do here in B is these are not like terms, so I can't add them together. But what I can do is I can use my happy little rainbows, my distributive property, and multiply both radicals by that. So I have the square root of 3 times the square root of 3 minus the square root of 3 times the square root of 7. Now, just so that you know where everything comes from, I'm going to use colors here. So 7 is the same as this 7. This 3 is the same as, or this root 3 is the same as this root 3. And this root 3 is the same as both of these. Okay, so we've distributed that root 3 to both of those terms. Root 3 times root 3 is simply the number 3 minus root 3 times root 7 is the square root of 21. Now, do I have any perfect square factors here? Do I have 9s? Nope. Do I have 4s? Nope. 16? Nope. 25? No, that's too big. So this is actually my final answer. This one gets a little bit tricky because we need to use our happy little rainbows twice. So I'm just going to go like this. So this is going to be really a long written out thing. Okay, so I'm going to color code here. So I'm going to multiply this by this and this. And then I'm going to multiply this guy by the 2 terms in the second bracket. So here I go, and I'm going to color code in a little bit. So 4 root 2 times 3 root 2. So I've done this step. The next one is, I'm going to be subtracting, so minus 4 root 2 times root 5. Now I'm going to distribute this one, plus 2 root 5 times 3 root 2 minus 2 root 5 times root 5. Now, yes, I'm going to color code everything. So all my 4 root 2's, they're because of the 4 root 2 in this one. And all of my 2 root 5's are because of the 2 root 5's in the first bracket, the second term in the first bracket. And now I have my 3 root 2, 3 root 2, and then I have my root 5. And that's the reason why these are negative is because of the root 5 here. Now what I'm going to do is I'm going to multiply number to number and radical to radical. So 4 times 3 is 12. Root 2 times root 2 is 2. Minus 4 times the coefficient in front of this one is 1, so it's 4 times root 2 times 5 is 10. Plus 2 times 3 is 6. Root 5 times root 2 is root 10. Minus 2 times 1 is 2. Times the square root of 25, but we know that that is simply times 5. So we're multiplying this by 5. Now I can simplify a little bit more. 2 times 12 is 24, minus 4 root 10 plus, why did I write root 2? Root 10 plus 6 root 10 minus 10. 2 times 5 is 10. So that is 24 minus 10 is 14. Negative 4 of some quantity plus 6 of some quantity, that some quantity just happens to be root 10, is going to be plus 2 of that quantity, root 10. Done. Now this one is a really special one. The word that is going to come up is conjugate. And you'll see why, since I know that this is the conjugate of this, I can do the happy, happy dance of joy. The math dance of joy, that is. So, we are going to distribute this both ways. And this one we're going to distribute as well. There'll be less color coding in this one, so if you didn't quite understand the one above it, why don't you just pause, go back and re-watch it, because this one I'm going to go a little bit faster. So I'm saying 4 root 2 times 4 root 2 minus 4 root 2 times 2 root 3 plus 2 root 3 times 4 root 2 minus 2 root 3 times 2 root 3. So I have 16 times 2, root 2 times root 2, minus 8 times root 6, plus 8 times root 6, minus 2 times 2 is 4, root 3 times root 3 is 3. So here I have 32 minus 8 root 6 plus 8 root 6 minus 12. Look what happens here. If I highlight this one, what happens to that middle term? Ah, yes. It turns into 0 because I have negative 8 of root 6's and then I add 8 root 6's. So that becomes 0. And then 32 minus 12, simply put, is 20. And we're done. So what we love about the conjugate, so before actually that, what does this remind you of? What kind of factoring? It kind of reminds me personally of a difference of squares. Because if I said A plus b, a minus b, is a squared minus b squared. Whereas if I would say a plus b times a plus b, I would get a squared plus 2ab plus b squared. Because it's a difference of squares, that middle term actually goes away, just like the middle term in this goes away. So more about that later, but keep that in the back of your head.